तमिलनाडु,
ठीक है,
पंजाब, हरियाणा,
गुड 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 गुड
बिहार,
गुड,
सभी जगह से हैं सर पार्टिसिपेंट्स। यस सर।
वेरी गुड वेरी गुड वेरी गुड वेरी गुड।
जम्मू कश्मीर, यस सर, यस सर।
अच्छा, जम्मू कश्मीर से भी आए हुए हैं?
जी सर, जी सर, जम्मू कश्मीर से भी हैं सर।
गुड गुड गुड।
So welcome back in the afternoon in the third session of the day। आज के तीसरे सत्र में आप सभी का स्वागत, अभिनंदन। हमारे साथ इस सत्र में प्रोफेसर S.C. अरोड़ा जी जुड़ चुके हैं। मैं रिक्वेस्ट द पार्टिसिपेंट्स टू स्टार्ट द प्रोग्राम। मेरा प्रतिभागियों से अनुरोध, वह कार्यक्रम को शुरू करें। विनोद जी, या
Yes, sir. I'm audible, sir.
ऑडिबल।
Audible.
चलिए,
Yes, sir.
ऑडिबल
ऑडिबल
ऑडिबल।
विनोद जी।
Good afternoon to all of you. Myself, Dr. Vinod Kumar, Assistant Professor in Mathematics, Government College, Baroda, Sonipat, Haryana. Firstly, I am thankful to CPDHE New Delhi to give this opportunity, and it is pleasure to me to introduce Professor S.C. Arora, retired professor in mathematics from Department of Mathematics, University of Delhi. Is born in 1945. Professor Arora has completed his BSc, MSc, and PhD degree from University of Delhi and has a 48 years of teaching experience. He has published 108 research papers in various national and international journals and has organized many national and international conferences at DU. He has published a book on the topic, a textbook of calculus. He has guided 75 scholars of MPhil and PhD. Professor Arora attended various national, international conferences and delivered a talk at international conference at Bulgaria. Also, he has visited Dubai, Oman, Bhutan for various assignment of education. Professor Arora has a long experience of administrative, like head of the department at DU, coordinator of the CPDHE New Delhi, member of the governing body, academic council, advisory committee, and managing committee of the various universities in India. He has been awarded by guest of honor by different colleges and universities. On behalf of CPDHE, I invited Professor Arora sir to deliver his lecture. Sir, please.
आपका स्वागत, अभिनंदन है सर इस संस्थान में।
Thank
Yes, sir.
you, Vinod Kumar ji. Thank you for the
Thank you, sir.
nice words that you have used for me. In fact, in short, I must say that all these achievements, whichever you are talking about, they are based upon just one thing. That was
Yes, sir.
going to the class and taking the class regularly. Nothing
Yes,
else. Everything else is a corollary to that theorem. That
yes,
I
yes, sir.
used to go to the class regularly every day, not missing any lecture. All these, say, member of this thing, member of that, the governing body of that college, and visited that university, this university, they are all consequences of that thing only. And that is my
Yes, sir.
achievement, that I was very regular in my teaching to the students. But in any
Yes, sir.
case, I must pay regards to the CPDHE, Dr. Sachin Vashisht, and the management CPDHE for inviting me to deliver a lecture on fundamental theorem of algebra. Of course, I will deliver two lectures, 1 and 2. At this,
You may start, sir.
a teacher is teaching a class, undergraduate class, first year class, and is doing this theorem. that every equation of nth degree possesses n and only n roots. She begins like that, that suppose there is an equation, say a naught plus a1x plus a2x square plus so on plus a n x n is equal to 0 is an equation of nth degree where a n is not equal to 0. And begins like that. So let alpha 1 be a root of this equation. Then this equation, which I write as fx is equal to 0, can be written as f of x is equal to x minus alpha 1 into some f1x. Again, f1x is equal to 0 is an equation of n minus 1 degree and will possess one root, say alpha 2. And therefore f1x can be written as f1x is equal to x minus alpha 2 into f2x. And so fx is equal to x minus alpha 1 into x minus alpha 2 into x minus alpha n, and so on, so on, so on, like that, you see. And say that fx is equal to an into x minus alpha 1 into x minus alpha 2 into x minus alpha n, and says it shows that alpha 1, alpha 2, alpha n, they are the roots of this equation. And suppose beta is any other root which is not equal to alpha I for any I, then f of beta is equal to an into beta minus alpha 1 into beta minus alpha 2 into beta minus alpha n, which is not equal to 0. And therefore there is no other root. And that means this equation of nth degree fx is equal to a naught plus a1x plus a2x square plus a n x n is equal to 0. So there is n and only n roots, and finishes the proof. Everybody becomes happy, see, with this proof, including the student and the teacher. But there are some who are unhappy. Who are unhappy? Person like me are unhappy and ask this question, that why the teacher should suppose that alpha 1 is a root of the equation fx is equal to 0. What is the right of supposing? Who has given the right to assume that let alpha 1 be a root of this equation? See, this equation possesses a root or doesn't possess a root. This is what the fundamental theorem is. What the theorem is? What the theorem is, I'll tell you. The statement of fundamental theorem of algebra says every non-constant polynomial with complex coefficient has a root in the set of complex numbers. Or every equation of every equation which is of course a non-constant equation with complex coefficient has a root in the set of complex number. See, equivalently, this statement is that every polynomial of degree n greater than or equal to 1 over the field of complex number has n and only n roots. There are many equivalent statements, and they are every polynomial of degree n greater than or equal to 1 over the field of complex number can be expressed as a into z minus alpha 1 into z minus alpha 2 into z minus alpha n. Thus, if Pz is equal to Zn plus An minus 1, Zn minus 1 plus so on plus A1z plus A naught is a polynomial where the coefficients A naught, A1, An minus 1 are real or complex number, then there exists a complex number alpha such that P of alpha is equal to 0. See, there are many equivalent formulation of this problem. The equivalent formulation of the problem are the following. Number 1, every non-constant polynomial with real coefficient, not complex, real coefficient, can be expressed as product of real linear or real quadratic factors, because every polynomial with real coefficient has a complex root, because every polynomial with real coefficient can be considered as a polynomial with complex coefficient. Therefore, that must possess a root. And ultimately, when the second degree equations they are obtained, they can have complex roots. And then second formulation is, for each n greater than or equal to 1, every n cross n square matrix over the field of complex number has an eigenvector. hence an eigenvalue. That is, every linear operator on an n-dimensional complex vector space has an eigenvector. I'll firstly justify that these are, see how these are equivalent formulations. The arguments are the following. See, next is the arguments are the following. Firstly, how fundamental theorem of algebra see equivalent to 1. How? Because if FTA is proved, that is, every polynomial with complex coefficient has a root in the set of complex numbers. See, if FTA is proved, I'll name it as FTA every time. If FTA is proved, that any polynomial with real coefficients can be treated as a polynomial with complex coefficients and can be therefore factored into quadratic and linear factors, and also realizing that any real quadratic will have complex roots in conjugate pairs, because you know every equation, every quadratic equation with real coefficient has say complex root in conjugate pair. Again, if one is proved, then given any polynomial pz with complex coefficient, then one can construct a polynomial with real coefficient as pz into pz bar is equal to 0. That is pz mod square is equal to 0. Eh? Now, any root of the resulting polynomial will either be root of the original polynomial or the complex conjugate of a root. And that implies that this is the FTA is equivalent to 1. Now, how FTA is equivalent to 2? Suppose FTA is proved, then suppose we have a square matrix A naught, A11, A12, A1n, A21, A22, A2n, and AN1, AN2, ANN. Suppose this is any n cross n square matrix over the field of complex numbers. I consider Zi minus A mod is equal to 0, which becomes equal to Z minus A11 minus A12, and so on, minus A1n, minus A21, etc. See, that is before you. See, minus AN1, AN2, and Z minus ANN is equal to 0. If I open this will be a polynomial, which is fz is equal to Zn plus an minus 1, Zn minus 1, plus so on, plus a1z plus a naught is equal to 0. So if lambda is the root of this equation, then lambda I minus a is singular. Singular matrix means which is not invertible. And therefore, if that is not invertible, therefore that is not 1, 1. That means that will take a non-zero vector to 0. That means there exists some x not equal to 0, such that lambda I minus a of x is equal to 0. That is ax is equal to lambda x. And that gives you, see, that every lambda being an eigenvalue, that means every square matrix has an eigenvalue. Conversely, suppose second is true. Then we consider any polynomial fz is equal to zn plus an minus 1, zn minus 1 plus so on, plus a1z plus a naught for n greater than or equal to 1. And of course, all these AIs, they belong to C. We claim by induction, which I'll take for firstly for n equal to 1, we claim that determinant of lambda I n minus a is equal to f of lambda, where f lambda, where a is this matrix, where a is equal to 0, 0, see this matrix being constructed 0, 0, 0 minus a and naught, 1, 0, 0 minus a1, and so on this one. See, what will be for n is equal to 1? That would be 1 cross 1 matrix. That would be, that is minus a naught only. And then we take a is equal to minus a naught, 1 cross 1 matrix. And when I take lambda I minus a, that would be lambda I plus a naught. That means lambda plus a naught, and that is equal to f lambda for n equal to 1. For n equal to 2, fz is equal to z square plus a1z plus a naught. That becomes a polynomial of second degree. And a we take as 0 minus a naught, 1 minus a1. And lambda I2 being 2 cross 2 unit matrix, lambda I2 minus a is equal to lambda a naught minus 1 lambda plus a naught, which when I open it, it is lambda square plus a1 lambda plus a naught, and that is equal to f lambda. For suppose for n, no, this shows that the result is true for n is equal to 2. And suppose for n minus 1, the result has been proved. Then if fz is equal to zn plus en minus 1, zn minus 1 plus e1z plus a naught, f lambda therefore becomes equal to lambda n plus en minus 1 lambda n minus 1 plus e1 lambda plus a naught. Now if I consider a to be equal to this matrix 0 0 0 0 minus a naught, 1 0 0 0 and minus a1 0 0, and this is 1, and then this is 1 minus 1 and minus en plus 1, they are separate. Then sorry, en minus 1 separate. Then lambda I minus a determinant is equal to this determinant lambda 0 0 0 a naught minus 1 lambda 0 0 0 plus a1 0 0 0 minus 1 lambda, and when I open this, this becomes equal to f lambda. When I open with the first one, the first diagonal, first column, it is lambda into lambda 0 0 0 a1 minus 1 lambda 0 0 a2 and 0 0 0 minus 1 lambda plus a n minus 1, which by induction, because I have already assumed that the result is true for n minus 1, this would be plus minus 1 a naught into this, and when I open this out, this would be lambda of the first determinant and minus 1 a minus 1 a naught, and that would be only the 1. The second determinant, the value of the second determinant is just 1, and it would be in fact minus 1 a raised to power n minus 1, and which would become 1 only. And because the result has been assumed to be true for n minus 1, so the value of this determinant would become equal to lambda n minus 1 plus a n minus 1 lambda n minus 2 plus so on plus a1 plus a naught, and which will finally on computation will become equal to f lambda. Therefore, determinant of lambda I minus a is equal to f lambda. Therefore, if a has a characteristic vector, then for some lambda, determinant of lambda I minus a is equal to 0. Therefore, f lambda has a root in the set of complex numbers. This shows that fundamental theorem of algebra is equivalent to those two statements. That is, that any polynomial over real coefficient or any square matrix has characteristic root and characteristic value. Now, I come to history of fundamental theorem of algebra. That when people started, mathematicians started talking about fundamental theorem of algebra, some versions of the statement of fundamental theorem of algebra first appeared early in the 17th century in the writings of several mathematicians, including Peter Roth, Albert Girard, and René Descartes. All these mathematicians believed that the polynomial equation of degree n must have n roots, and the only problem was they believed to show that these roots lie in the set of complex numbers. In 1702, a proof that FTA was false was given by Leibniz in 1702, when he asserted that z raised to power 4 plus x raised to power 4 plus t raised to power 4 could never be written as product of two real quadratic factors. His mistake came in not realizing that root I could be written in the form of a plus ib, where a and b are real. Then came the year 1742. Euler, in the year 1742, in correspondence with Nicolaus II, Bernoulli and Goldbach showed that the Leibniz counterexample was false. In 1746, Jean-Louis d'Alembert, same Alembert's ratio test, this is same Alembert, in the year 1746, made the first serious attempt at a proof of fundamental theorem of algebra. He published his proof in Researches sur la calcul integral history academic science Berlin 2 1746 182 to 224. Proof given by D. Lambert was not very rigorous and had several weaknesses. He used the following lemma. Suppose f is a non-constant polynomial and fz naught is not equal to 0. Then for every epsilon greater than 0, there exists some z such that z minus z naught mod is less than epsilon and fz dot mod is less than fz dot mod. This, of course, lemma, now, of course, it is proved, but at that time it was unknown. D. Lambert's proof of this lemma was not very rigorous, and it was unnecessarily complicated. A simpler proof of the lemma was given by Jean Robert Argand in 1806. Furthermore, he also used that a continuous real valued function on a compact set achieves a minimum value, a fact that had yet not been rigorously proved in D. Lambert's lemma. Therefore, proof given by D. Lambert in 1746 was not convincing. Although now we know all these things, but say some 300 years back, it was not. In 1749, shortly after D. Lambert's proof, Leonard Euler published an algebraic proof of FTA by attempting to prove that every polynomial of nth degree with real coefficient has precisely n zeros in the set of complex numbers. In 1772, Joseph Louis Lagrange, in the year 1772, raised many objections to Euler's proof and pointed out many gaps. He used his knowledge of permutation to fill all the gaps in the Euler proof. However, one significant gap still remained. Euler and Lagrange both assumed that a polynomial of degree n would have n roots and that the only thing to be proved is that these roots are complex numbers. In 1795, Laplace, in the year 1795, tried to prove the FTA using a complete different approach, using the discriminant of a polynomial. His proof was quite elegant, but unfortunately, in his proof also, the existence of roots was assumed. Then came the crucial year 1799. Please, why I say this to be crucial here? Because that was the year when fundamental theorem of algebra was proved by whom? Uh, uh, by Carl Friedrich Gauss. In 1799, the first person to notice these gaps was Carl Friedrich Gauss. He is credited with producing the first correct proof in his doctoral dissertation, which he submitted in the year 1799. About Euler-Lagrange proof, Gauss says the following. If one carries out operations with impossible roots as though they really existed and says, for example, sum of all the roots of this equation is equal to 0, that's xm plus axm minus 1, etc. is equal to 0, is equal to, and that sum is equal to minus a, even though some of them may be impossible to exist. Because they were assuming that the roots exist, the only thing that we want to prove that they lie in the set of complex numbers. This is Gauss commented that, see, you are assuming something, and see, the existence of which is not established so far. See, which really meant even if some are not existent and therefore missing, then I can say that I thoroughly disapprove this type of argument. Gauss himself did not claim to give the first proper proof. He merely called the proof was new. About D'Alembert's proof, despite his objection, he said a rigorous proof could be constructed on the basis of D'Alembert's line. Gauss' proof of 1799 was topological in nature. However, it does not meet our present day standards of a rigorous proof. Now we do mathematics very rigorously, but at that time these tools were not available, and therefore some of the assumptions were made, which of course might not be true, but still it continued. But then in 1814, Jean Robert Argand published a proof based on D'Alembert's 1746 idea and was the simplest of all the proofs. Gauss himself, throughout his lifetime, kept on working over FTA, and 2 years after Argand's proof, Gauss in 1816 published a second proof which was complete and correct. In 1816 itself, Gauss gave third proof of the FTA, and 1849, on the 50th anniversary of his first proof, gave the fourth proof of the FTA. Since then, and even before, many mathematicians across the globe have been working over the theorem and have been publishing various proofs using tools from various branches of mathematics. More than 100 proofs have come so far, and the recent most in 21. See, this is 20 is type, but it is 21. In 21 itself is established. In 2021, a proof of the fundamental theorem of algebra using Hurwitz's theorem, see it by Mahmoodi and Muhammad Gol Golmazadeh, see Elements of Mathematics 76C 2021, number 138 to 39. Many mathematicians who got attracted by the problem and contributed to the solution of the FTA include the following. I present here see some of the mathematicians who have given different proofs in different years. Kindly pay attention to that how much important this theorem was, and how people from all over the world were contributing to this problem, that every equation of nth degree possesses n and only n roots. Every polynomial nth degree over the field of complex numbers has n zeros in the set of complex numbers. You see, this simple theorem, see, got the attraction of the mathematicians, see, all over the world. Please, here is the list which I read uh, uh, quite see, briskly before you, but you should know that the contribution given by different mathematicians. I begin with 1746. It is Jean Lee Ron D. Albert. Researches sur la calcul integral, history, academic sciences, Berlin, 182 to 224. Leonard Euler, 1749, researches sur la racine imaginaries, thus equation, and so on, reprinted in Opera Omania series Prima, volume 6, 78 to 147. The Joseph Louis Lagrange, sur la form, thus racine imaginaries, the thus equation, the academic Berlin, reprinted in Yavers, volume 3, 479 to 516. Carl Friedrich Gauss, 1799. This was Demonstratio Nova Ultra Theorematics Omen, etc. He reprinted in work volume 3, 1 to 30. Then fifth is Argon, 1806. This is Isai Sir Une. This is the collection. Manra, the representation, less quantities, imaginaries, etc. Geometric, Paris, 1806. Mm. Then Carl Friedrich Gauss, 1816. Demonstratio Nova Ultra Fermat Omnum Functionum Algebra, etc. This is reprinted in work volume 3, 51 to 56. Alexandra Ostrovsky, 1920. through Wade, Dan Estrom, and Gaussian Davis, the part two, the, then R. Boyce Jr., 1935, A Proof of the Fundamental Theorem of Algebra, American Mathematical Monthly, 42, 501 to 502. Then N.C. Ankeny, one more proof of 1947, one more proof of fundamental theorem of algebra, American Mathematical Monthly, 54, 8, 1947. Raymond Redifer, 1957, The Fundamental Theorem of Algebra, American Mathematical Monthly, 64, 582 to 585. Then R.M. Redeffer, 1964, What Another Note, just on the Fundamental Theorem of Algebra, American Mathematical Monthly, 71, 180 to 185. Then R.P. Boyce Jr., 1964, Yet Another Proof of the Fundamental Theorem of Algebra, American Mathematical Monthly, 71 to 180. Then S. Wolfenstein, Proof of the Fundamental Theorem of 1967, Proof of the Fundamental Theorem of Algebra, American Mathematical Monthly, in 1967. Then Charles Pfefferman, 1967, An Easy Proof of the Fundamental Theorem of Algebra, American Mathematical Monthly, 74, 854 to 855. Then Fraud Turkleson, 1976, The Fundamental Theorem of Algebra, American Math Monthly, 83, 647. Then M. Dodson, 1984, A Brouwer Type Coincidence Theorem and the Fundamental Theorem of Algebra. See, Commode Math Bulletin, 27, 4, 1984. Then A. Avian, 1986, A New Proof of the Fundamental Theorem of Algebra, Caribbean Journal of Math, 5, number 1, 9 to 12. John Stilwell, 1989, Mathematics and its History. Springer, this is a book, Springer Verlag, New York. Then A. Avian and James A. Wilson, 1990, A Theorem Equivalent to Theorem of Algebra. The Nice Arc with 84, etc. Then William Dunham, 1991, Euler and the Fundamental Theorem of Algebra, College Math, and so on. Joseph Banish, 1992, Another Proof of the Fundamental Theorem of Algebra, American Mathematical Monthly, 99 to 46. Javier Gomez Calderon and David M. Wells, 1996, Why Polynomials Have Roots, College Math, Journal 27, 1991. Daniel A. Wellman, Another Proof of the Fundamental Theorem of Algebra, Math Magazine, see, 70, 216, 217. Daniel J. Wellman, The Fundamental Theorem of Algebra, A Visual Approach, unpublished. This was unpublished, but it came into existence. About this proof, I must add to it, it was a proof where each complex number was given a color and the whole complex plane and where the black dot was there, that was the zero. And by visually, this is called a colored proof of fundamental theorem of algebra. It was given like that. You see, Benjamin Fine and Gerhard Rosenberger, 1997, The Fundamental Theorem of Algebra, Springer Verlag, New York. This book also contains 11 proofs. You see, this is the book. You see, published in 1997. Michael Day, Isser born, The Fundamental Theorem of Algebra, 1998, Algebra College Math. You see, John Boyle, 1999, A Simple Proof of the Fundamental Theorem of Algebra, International Journal of Mathematics, and so on. The Anindya Sen, 2000, Fundamental Theorem of Algebra, Yet Another Proof, American Mathematical Monthly, 3107. Then A.D. Mediors and S. Swan, The Fundamental Theorem of Algebra, Revisited, American Mathematical Monthly, 108. Then H. Dirksen, 2003, the Fundamental Theorem of Algebra and Linear Algebra, American Mathematics Monthly. Then Conrad, the Fundamental Theorem of Algebra via Linear Algebra, modification of the proof by H. Darkshan. Then Nihal and Pasu in 2005, a probabilistic proof of fundamental theorem of algebra via probability. This proof was given. You see, Proceeding American Math Society. In this journal, it was published. Then A. Tagavi, 2006, a proof of fundamental theorem of algebra. You see, in 2006 it was given. Anton Arshap, 2009, a simple complex analysis and an advanced calculus proof of fundamental theorem of algebra. American Mathematical Monthly, 116 January 67 to 68. Alan C. Laser, Mark Lockband, 2010, the fundamental theorem of algebra via the Fourier inversion formula. Then H. Harrop, 2011, relative equilibrium of point vertices and the fundamental theorem of algebra, proceeding of the Royal Society, a mathematical, physical, and engineering sciences, 2010. Then J.M. Almira and A. Romero, 2012, some Riemannian geometric proofs of fundamental theorem of algebra using differential geometry, of course, in dynamical systems. The proof was given. Then D. Oliveira and O.R. Branco, the fundamental theorem of algebra from the four basic operations, American Mathematics Monthly, 2012. Then Kalantri Bahaman, Torrance Bruce, the fundamental theorem of algebra for artists, mathematics horizon, like that. See, then it is 2014, Leo Bio Quinn, a direct proof and a transcendental version of the fundamental theorem of algebra via Cauchy's theorem, American Mathematics Monthly, 2014. Then Armentano, Diego, Shub, Michael, erratum to, see, this was, erratum to this paper, published in 2014. Then Vilenzanti, Darius M. on the fundamental theorem of algebra for polynomial equations over real composition algebra. See, it is 2014, number 7. Then Yunus A. Zetko and Q, the fundamental theorem of algebra and the divergence of reciprocals of primes, looked at, you see, in 2015. And then Wellman, the fundamental theorem of visual approach, you see, the Math Intelligence, 2015. Then Vikas Chakravarti, a simple proof of fundamental theorem of algebra, Math Student, 85, 2016. Then Soham Basu, Wellman, and J. Daniel on Gauss' first proof of fundamental theorem of algebra, American Mathematical Monthly, 2017, 688, 694. Then Mohsen Alai Badi, a note on the fundamental theorem of algebra, Bulletin Australian Math Society, 2018. Then Peng Liu Shivo on the subjectivity of smooth maps into Euclidean spaces and the fundamental theorem of algebra. It is the American Mathematical Monthly, 2018. Then Daniel Girela, a proof of fundamental theorem of algebra, Spanish, of course, it is 2018. Then Pedro Romero, another proof of fundamental theorem of algebra in 2018, and the Maths Gazette. Then V. Olga Kodos, one proof of the fundamental theorem of algebra. It is published in 2019. And then Daniel Perocchi, it is again 2019, quantitative fundamental theorem of algebra. Then Guzman, Ortin, Fobio, a proof of fundamental theorem of algebra by Giulio Grovitato. And this is lecture math 2019. Then Javarov, I.S. Hasanova, GK, on the fundamental theorem of algebra and its equivalence to the Frobenius theorem on Devian algebra, the 2019. Then B. Chakravarti, again proof given in 2019. And then Stephen Kranz, how fundamental is the fundamental theorem of algebra? Math Magazine 93 2020, number 2139142. Then Mahmoodi and Muhammad Ghulam Azad, they a proof of fundamental theorem of algebra using Hurwitz's theorem. See, Elements Math 76C 2021, number 1, 38 to 39. This, of course, is a very long list. You see, this is not the list of all the mathematicians working, but whatever I could collect, I have collected right from those days up to coming to 2021. Still, the work is going on. Work is not yet over. See, every day, see, every year, every month, every week, a new proof of fundamental theorem of algebra comes into, and see, that comes. And see, the list is very long. Of course, whatever is possible, that I have collected. See, all proofs of the fundamental theorem of algebra necessarily involve some analysis, or more precisely, the concept of continuity of real or complex polynomial. We mention broadly speaking, all the proofs of fundamental theorem of algebra, you know, can can be classified into 5 different approaches: complex analysis, topology, algebra, probabilistic, and visual. See, this visual proof by Wellman, I was mentioning to you, you know. So, but they can be classified like that. See, at the moment, because at the moment, I'm to talk. See, to address. I'm strict to complex analysis. I give firstly one proof based on complex analysis only. This proof, this proof is based on the use of a classical theorem of Picard. Picard theorem says that, see, this is Picard theorem. Picard theorem. 245. Picard theorem says that if there are two distinct values in the complex plane, which a given entire function never assumes, if the two distinct values, a given, if there are two distinct values in the complex plane, a given entire, what is an entire function? A function is said to be entire if it is differentiable throughout the complex plane. That function, for example, a polynomial. A polynomial is a function, a complex valued function, differentiable throughout the complex plane. Sin z, cos z, they are entire function. So Picard theorem says, if there are two distinct values in the complex plane which a given entire function never assumes, then the function is constant. That is what it says. See, proof of fundamental theorem of algebra. See, what I am to talk about, you see, suppose fz is equal to zn plus an minus 1, zn minus 1, plus so on, plus a1z plus a naught, n greater than or equal to 1, and ai's are constant. It is a non-constant polynomial. And what I am to prove, that there exists some z such that fz is equal to 0. There exists some z in the set of complex numbers. Let if possible fz be not equal to 0 for any z in the set of complex numbers. Then this means what? This means, see, what is that we claim? We claim fz fails to take on one of the values 1 by k equal to 1, 2, and so on. Suppose for each k, fzk is equal to 1 by k. Suppose for each k, this value 1 by k is attained. That means there would exist some zk such that fzk is equal to 1 by k for each k. That means we have got, kindly excuse me, I'll like to take a glass of water. Huh? Kindly, see pause for, थोड़ा पानी दो। हाँ हाँ I hope I am audible to everybody.
Yes, sir. Yes, sir.
Yes,
Audible,
sir.
sir.
Yes,
Audible,
sir.
sir.
Audible.
Audible.
See, fz fails to take on one of the values 1 by k for any k. Suppose for each k I get that there exists some zk such that f of zk is equal to 1 by k. That is, f of zk is equal to 1 by k for k equal to 1, for 1 f of z1, for 2 f of z2 is equal to 1 by 2, f of z3 is equal to 1 by 3, f of z4 is equal to 1 by 4. Suppose that happens. That means we have got a sequence. Then we have the f of, excuse me for 1 minute, please. That means f of zk is equal to 1 by k. Then we have f of z mod. This is a polynomial. F of z mod is equal to, the polynomial was an zn, an yes, it was an plus an minus 1 zn minus 1 plus so on. I take z mod n common, so fz mod is equal to z mod n, and in the modulus it is 1 plus an minus 1 divided by z plus an minus 2 divided by z square plus so on, plus a naught zn modulus. Clear? So what happens to this absurd when z tends to infinity? That means z mod tends to infinity. See, look at what happens in see inside the modulus. En minus 1 by z will tend to 0. En minus 2 by z square will also tend to 0. A naught by zn will also tend to 0. Their sum will also tend to 0. 1 plus en minus 1 divided by z plus en minus 2 divided by z square plus so on, plus a naught zn mod will tend to 1, and z mod n tends to infinity as z mod tends to infinity. So finally, what is that we obtain? We obtain fz mod tends to infinity as z mod tends to infinity. This is what we get. Look at fz. Fz is our polynomial, that usual polynomial. En, we want to prove that there exists some z such that this is equal to 0. We are assuming otherwise, that no zero is not attained. 0 is not attained, and then our claim that fz fails to take one of these values 1 by k. But if that happens, then fz mod tends to infinity as z mod tends to infinity. See, by definition of tending to infinity, it means that there exists some capital R greater than 0 such that fz mod is greater than 1 for all z satisfying z mod greater than R. This follows by the definition of when fz mod tends to infinity. And that means, this means that, but if we consider the complement of this, that is, although z such that z mod less than or equal to R, this is what? This is a closed bounded disk. It is a closed and of course bounded also. Therefore, these, see, if we consider this, these see this disk, although z such that z mod less than or equal to R, this is closed and bounded, and our sequence zk, they have a limit point. That is, there exists a subsequence z and I such that z and I tends to some z belonging to this disk. As f is continuous, f of z and I tends to fz, right? So fz is what? Limit of f, z and I. And z and I is tending to this. So f, and that is equal to, but f of z and I is nothing but limit of 1 by k and I, and that is tending to 0. So limit of that is equal to 0. That means fz is equal to 0. And therefore, because we are assuming fz is not equal to 0, and therefore fz fails to take on the value 1 by k for some k. We were assuming otherwise, we reach a contradiction. Therefore, fz fails to take on the value 1 by k for some k. Now, fz is not equal to 0. That means 0 is also not attained. See, and fz fails to take one of the values. That means two different values are not attained by this function fz. And Picard theorem says in that case f becomes a constant function. See, now fz is not equal to 0 for each z, and fz is equal to not equal to 1 by k for each z, and f is entire, f, because every polynomial is an entire function, so f must be a constant function. By Picard's theorem, a contradiction, because degree of fz is greater than or equal to 1, it is non-constant, and therefore this proves that there exists some z naught such that, you know, such z naught belong to C, such that fz naught is equal to 0. Right? So my what is time?
This is almost 3 now, 2:53.
2:53.
Yes.
So we can begin with the next lecture, and I'll then of course adjust accordingly. The next
Next lecture.
next lecture.
Okay. Baat karo.
I continue with the applications of fundamental theorem of algebra. Next whole page.
Vinod sir, you are the chairperson.
Yes, sir.
I continue with application.
Visible, sir. Visible, sir.
Visible?
Yes, sir.
Okay. The fundamental theorem of algebra, particularly its equivalence to determining eigenvalues and eigenvector. I told you the equivalence to it is equivalent to determine eigenvalues, eigenvectors. That every square matrix has got eigenvalue. What is an eigenvalue? If suppose A is a square matrix, then lambda is said to be an eigenvalue if there exists some x not equal to 0, such that Ax is equal to lambda x, and x in that case is called corresponding eigenvector. So I told you in my lecture that talking about fundamental theorem of algebra is equivalent to determining eigenvalues and eigenvectors of a square matrix. See, so fundamental theorem of algebra, particularly its equivalence to equivalence to, you know, determining eigenvalues and eigenvectors of a square matrix, and subsequently reducing the square matrix to diagonal form. What is the diagonal form of a matrix? Diagonal form is that suppose A, which is when a square matrix n cross n is said to be, you know, in diagonal form. See, when we have non-diagonal non-diagonal elements are equal to 0. That is, A is equal to lambda 1 0 0 0, 0 lambda 2 0 0 0, and so on 0 0 0. So every square matrix can be reduced to in using eigenvalues, and say uh, uh, every non-invertible square matrix can be reduced to diagonal form. So reducing the matrix to diagonal form, in that form, fundamental theorem of algebra, because they are all equivalent, it can be, you know, it has large application, you know, to broad range of sciences, square matrix to diagonal form, and has lot of application to broad range of sciences, physics, chemistry, biology, quantum mechanics, economics, and of course mathematics itself. So I firstly discuss the application of fundamental theorem of algebra using this thing, and then of course I'll come to more applications. Firstly, problem 1. Two herds of vicious animal. There are two type of vicious animal. They are fighting with each other, and so much fighting that they are killing each other. and say by two herds of vicious animals are fighting each other to the death. During the fight, the populations xt and yt of two species, the xt of one space and yt of the another space, can be modeled by the following system of equations. dx by dt is equal to minus 4y and dy dt is equal to minus 4x. Show that species won the fight given that y0 by x0 is less than half. What is y0? It is the existence of the species at the time t is equal to 0, and x0 is the existence of the species x1, first one, at the time t is equal to 0. This is less than half. Then they are t at any point of time, dx by dt is equal to minus 4y and dy by dt is equal to minus x. Show that the species 1 wins the race, wins the fight, given by y0 by x0 is less than half. Well, I've solved it by using, of course, fundamental theorem of algebra. Look at this equation. These equations can be written like that. dx by dt is equal to 0x minus 4y and dy by dt is equal to minus x plus 4y, which can be written as dx by dt over dy by dt. It is, you see, 2 cross 1 matrix is equal to 0 minus 4 minus 1 and 0 xy. See, this is in the matrix form. That means it is dv by dt is equal to av, where a is this matrix 0 minus 4 minus 1 0 and v is xy, and of course dx by dt is equal to dy by dt. By fundamental theorem of algebra, 0 minus 4 minus 1 0, you see, it will have two eigenvalues. How it will have two eigenvalues? 0 minus 4 minus 1 0 minus lambda into identity matrix, and if you solve that equation, see, you will get a quadratic equation. If you solve that equation, you will get two eigenvalues, 2 and minus 1, and the corresponding eigenvectors by of this square matrix are minus 2 1 and 2 1. That means a of 2 is equal to, you know, this eigenvector 2 into this eigenvector, and a of minus 2 is minus 2 of a of x is equal to this one. Okay. So next is, so if we take matrix S to be equal to the matrix, this is by eigenvectors, minus 2 1 eigenvector and 2 1. This matrix, of course, the inverse of this matrix, of course, I have determined, and it will come to, you know, S inverse is equal to minus 1 by 4, 1 by 4, 1 by 2, and 1 by 2. You see, there are many ways of determining inverse of a square matrix. See, you take its determinant and see 1 by adjoint A into multiplied by 1 by determinant of A will give you the inverse of this matrix, and like that. So if you take the determinant of this is minus 2 minus 1 by 4. That means we will be dividing by minus 1 by 4 and taking the adjoint of this, adjoint of S, and dividing by, you know, the determinant of this matrix, we will get inverse of this. So, but then S inverse AS becomes the diagonal, you know, diagonal matrix 2 0. These are your eigenvalues, 2 and minus 2, 2 0. S inverse AS is equal to, these are all applications of fundamental theorem of algebra. You see, because you can reduce the matrix to 2 0 0 minus 2, and S inverse AS becomes equal to this one. Therefore, A will become equal to, see, because S inverse AS is equal to 2 0 0 minus 2, pre-multiplying by S and post-multiplying by S inverse, we get A is equal to S 2 0 0 minus 2 S inverse. Now, in the differential equation, we can see, look, the differential equation therefore can be written. Look at the differential equation. Differential equation was dx by dt or dy by dt is equal to this matrix into xy. So this differential equation therefore would become, you see, dv by dt is equal to replacing a by s 2 0 0 minus 2 s inverse b. This is the original differential equation. And that means, this means it would be d of multiplying by uh, pre-multiplying by s inverse, and see, it would be d of s inverse v t. D of s inverse v dt is 2 0 0 minus 2 of s inverse v. Okay, that means d of s inverse v over dt is 2 0 0 minus 2 minus 1 by 4, the value of s inverse, minus 1 by 4, 1 by 4, 1 by 2, 1 by 2 of xy. We have reduced the given differential equation to this differential equation, where s inverse v is 1 by s inverse v is 1 by 4, 1 by 2, 1 by 4, 1 by 2 xy, which when I open it out, this is minus 1 by 4 x plus uh, x plus y by 2, and then x by 4 plus y by 2. Clear? See, so this means d of minus 1 by 4 x minus x by 4 plus y by 2 of second is x by 4 plus y by 2 is equal to 2 0 0 minus 2 and minus 1 by 4 plus y by 2 x by 4 plus y by 2. That is, writing the two differential equation, d of minus x by 4 plus y by 2 is equal to 2 of minus x by 4 plus y by 2, and then d of ddt of x by 4 plus y by 2 is equal to minus 2 of x by 4 plus y by 2. Look how that given differential equation I have reduced to differential equation of this type, where of course now the variable is minus x by 4 plus y by 2, and see one differential equation, and in the second x by 4 plus y by 2. I hope it is clear. If the given two different system of differential equation, I have reduced to these first order two differential equation, which of course you know simple solution, dx by dt is equal to 2 of dx. See, what is the value? Dx by x is equal to 2 of dt. It is the log of 2x is equal to this, and 2x is equal to e raised power. That is the solution. This is of that type. But the only difference is that the variable this time is minus x by 4 plus y by 2 in the first differential equation, and in the second differential equation, the variable is x by 4 plus y by 2. So therefore, what the solution is? Solution is, you know, minus xt by 4. The solutions of these two differential equations, you know, is minus xt by 4 plus yt by 2 is equal to minus x0. See, because when xt is equal to see that constant into some constant c into e raised to power 2t, then putting t is equal to 0, that becomes equal to x0, etc. So solutions are, see, minus xt by 4 plus yt by 2 is equal to minus x0 by 4 plus y0 by 2 into e raised to power 2t, and xt by 4 plus yt by 2 is equal to x0 by 4 plus y0 by 2 into e raised to power minus 2 and 2t. You can see that we have finally, using fundamental theorem of algebra, we have been able to solve, see, that system of differential equation. And at any time, see, these two species x and y, they are fighting with each other. At any time we have found out that minus xt by 4 plus yt by 2 is equal to minus x0 by 4 plus y0 by 2 into e raised to power 2t. This is at any time t. So we solve them. Therefore, yt is equal to minus x0 by 4 plus y0 by 2. See how to solve? You add firstly, when we add them, xt will cancel out. So yt will be equal to sum of these. And when I take the difference and difference of the first from second, I'll get xt. Xt by 2 I'll get to xt. So yt would be equal to 1 by 4 minus x0 plus 2y0 into e raised power 2t plus 1 by 4 x0 plus 2y0 into e raised power minus 2t, and xt is equal to 1 by 4 x0 plus 2. See, this gives that when those two species are fighting with each other, then the species 1 xt is 1 by 4 x0 plus 2y0 e raised power minus 2t, 1 by 4 x0 minus 2y0 e raised power 2t, and yt at any time t would be 1 by 4 minus x0 plus 2y0 e raised power 2t, 1 by 4 x0 plus 2y0 e raised power minus 2t. Now, we are given that 2y0 minus x0 is less than 0. 2y0 minus x0 is less than 0. That means if I take this species yt is equal to 1 by 4 minus x0 plus 2y0 e raised power 2t, and 1 by 4 x0 plus 2y0 e raised power minus 2. As time increases, e raised power minus 2t, tends to 0. And 2y0 x0 is given to be less than 0. And see this also. See, therefore yt, which is equal to this, see, this tends to 0 as t tends to infinity. As t tends to infinity, this tends to 0 because 2y0 minus x0 is less than 0. This keeps on decreasing. First term also keeps on decreasing. Second term also keeps on decreasing. See, the assumption is so made. The 2y0 minus x0, because this is negative, and e raised power 2t tends to infinity. That means this tends to minus infinity. That means this tends to 0. See, finally, see, so and so this tends to 0, and therefore this see, there would be a time when this will become equal to 0. What is that time? You can solve for t. It is log of something, e raised power 4t is equal to x0 plus 2y0 over x0 minus 2y0. That means t is equal to 1 by 4 log of this. At this time, y0 will be, yt will become equal to. So, but xt still is existent. That is, xt still remains greater than 0. Therefore, species 1 wins the fight. See, well, to the other to the other application, I'll come in my next
You can conclude.
to the other lectures, of course, we will come to see different applications, many more applications. See, in example one, of course, this matrix A is 2 cross. In general, in practical problems, the matrix may be n cross, है ना? Where what you will do, you will find the eigenvalue by fundamental theorem of algebra, reduce that to the diagonal form, then the matrix can be written as one vector in vector form, and therefore that can be solved. And see, again, respective differential equation would be obtained, and so on, like that. And more application. See, we apply fundamental theorem of algebra to find eigenvalues and eigenvectors to diagonalize the matrix A. See, for n equal to 1, etc., I'll come to the application, of course, next time. And here is the time to ask any question. You can ask problems, you can ask question, you can ask any doubt, you can ask things like that. I tell you fundamental theorem of algebra is very, very important in mathematics. See, people all over the world, they are talking about fundamental theorem of algebra. Of course, I have given at the moment only one application, but I'll give you more applications, But I will invite questions if there is any doubt. I'll ask you that kindly you can erase your doubts.
Any questions, sir?
Yes, विनोद जी पूछिए.
हाँ, any question? कोई? No, sir. I have no question, sir.
Yes, any questions? Komal ji, Kishore
Participant.
ji, Mohan ji. Yeah.
Hello, sir.
Hello.
Yes, Aruji.
Hello, sir. Would you please suggest some good book for this particular content, or especially for FTA? We can have
see,
study of
I
various
tell you,
versions of FTA.
I tell you, fundamental theorem of algebra, what the material that I have collected is only from internet.
Okay, sir.
Right?
Right.
I tell you, I have collected the material from internet.
Right, sir.
But there are books just on fundamental theorem of algebra. I have given also, when I gave you the list, some of the books I did mention.
Okay, sir. Yeah, okay.
These are the
I
books,
understand.
your fundamental theorem of algebra. Otherwise, fundamental theorem of algebra, using the other problems, can be solved in one page. And therefore, as such, you see, there are only 2-3 books which I mentioned, of course, in my references when I talked about. However, I have collected the material from internet, so to tell you the material about fundamental theorem of algebra.
Thank you.
I see these applications also. This is my collection. That these are the applications where I can talk about. For example, this problem itself, see, there were spaces xt and yt. Of course, the problem exists in differential equation, but I have transformed the whole thing, looking at that this is one of the applications of fundamental theorem of algebra. I don't claim that I have done any research work, nothing of that sort. It is only collection of the material from different books, from internet, from research papers, etc., etc.
Yes, sir. Okay, sir. Thank you, sir.
Yes, any other questions?
Any comment?
Yes, sir. You have
observation?
provided such a good collection in review of references. That will be really helpful for us. If you can share your PDF along with us, then that will be really beneficial, because at the same moment we are having.
Really no problem. See, this is not my research work. This is only collection of research work.
Yes, sir. Yes, sir.
You can give me your email. I'll send that. There is no problem as such. You see.
If you send it,
sir, you can
group,
send it to me, sir. I will send
you. You can give the email to Professor Sachin. No problem.
Yes, sir. Yes, sir.
No problem. He is in contact with me always. So he would be sending. I'll give the material to him. See, there is no problem as such.
Yes, yes.
But you will see more good material in the next lecture also. You will see that.
Yes, sir. Yes, sir.
I'll let you know. You will see next material, but I have retained that material for the next lecture, because that pertains only to application. You see, not the theory part, which I have stated, you see, in my first lecture.
Thank you.
Any other observation? Any other comment? I'll welcome. You see, any comment, any observation?
Yes.
Anything?
Any participant want to say?
Say something.
Or you may ask sometimes what kind of the problems you feel when you are discussing some topics in the classroom. On that also, if you are facing, because sir has a vast experience of teaching mathematics to the undergraduate as well as the postgraduate students. So in that way also you may ask.
You may ask me anything. I may not be able to answer. That's a different thing. But I'll try to answer.
Yes. Look at the age of 73 and 74.
Yes, sir. Yes, sir. Actually, what happens whenever we are teaching real analysis type, for example, real analysis, because that course will occur in most of the time in all of the university or all in the colleges. the either first or second semester courses. So at that time, students are not very good much about the real analysis or pure mathematics. They are having some sort of experience with the application part of it. They have some formulae, they apply the formula. So if you can suggest how we can introduce the real part so that the student can understand the because at that time this is the beginning of the students in real pure mathematics.
Suggest you two good books, you know. Number
Yes, sir.
one, see Principles of Mathematical Analysis by Walter Rudin. And then see Real Analysis by R.G. Bartle. These two are good books, you know. You see, you can have good account of real analysis.
Yes, sir, we are
remember
following these
when
books.
I taught in Hansraj College for 20 years, you know, Hansraj College, University of Delhi. For 20 years I taught. I used to teach real analysis, you know. Of course, I used to teach from Walter Rudin's book, you know. Walter Rudin's book. See, I learned, I should say, rudiments of analysis from Walter Rudin's book, you know. See, uniform convergence, and see Riemann integral, Riemann-Stieltjes integral, etc., you know. Good account of real analysis given out there. Complex analysis, Alfor's book, see Conway's book, then you see book by see one who has come to deliver lecture over here, Conway's book, Alfor's book, Churchill's book, you know.
Ponuswamy, sir, Ponuswamy.
Ponuswamy. Well, Ponuswamy, of course, was a help to me. But these three books, Churchill book, Alfor's book, and Conway's book, they were my so-called guidelines for teaching complex analysis. I taught complex analysis at postgraduate level for many years, you know. At Delhi University, of course, you know.
In presence,
case there is nothing to mention, so I pay thanks to you, you know, and see you next lecture. I'll begin whenever Dr. Sachin says, you know. Right. Okay.
Thank you, sir.
Thank you.